Okay, so let me start with something that happened recently in the United States. The Department of Energy issued an emergency order, and what the order said essentially was this: if things get bad enough on the electricity grid, we are allowed to cut power to data centers, not as a plan for a distant future, as an actual immediate option. I read this and I had to stop for a moment because think about what that means. The buildings that run our AI tools, our cloud storage, our emails, our streaming, our financial transactions, those buildings could be told you are using too much electricity. We are shutting you off so that ordinary households do not lose power. That is not what the story looked like in the news. It was a small item, a regulatory notice. But from a systems perspective, and that is the lens we use on this podcast, it is a significant signal. Something is under stress, and I want to explain what. Welcome to the Cascade. I am Omid Razbani. I'm an associate professor in systems engineering, and this is my attempt to take one story from the news every episode and show you what is really going on underneath it. Not the headline, the system behind the headline. Today, the system is the electricity grid, and the story is what happens when you plug the entire global AI industry into it. And I will say this up front. This story starts in the United States, but it does not stay there. By the end of this episode, I want to bring it to Norway, where I am based, and to show you that what is happening in America is also happening here, and honestly, in most countries that are part of the global digital economy. Okay, so now I want to explain why this happened. And to do that, I need to tell you about two systems that grew up separately, that were built on completely different logics, but that have now become deeply entangled with each other. The first is the electricity grid. It is old. Parts of it go back to the early 20th century, and it was built around a very specific assumption. The demand is predictable. People wake up, they use electricity. Factories run during the day. Evening comes, people come home, they cook, they watch television. You can model this. You can plan for it. The grid was engineered for a world with a stable and foreseeable rhythm of consumption. The second system is the internet, and the internet was built on a completely different logic. It was designed to be resilient, distributed. If one part fails, traffic reroutes around it. The whole architecture was built for uncertainty and surprise. Here's the irony though, and this is something I find genuinely interesting. The internet, this system designed to be resilient and distributed, runs on physical infrastructure that is extremely concentrated and extremely power hungry. Data centers are not abstract. They are very large buildings, full of servers and cooling equipment in specific locations plugged into the grid. And they consume electricity continuously at a scale that is getting harder for the grid to accommodate. And here's the part that really changes the equation: AI. AI workloads are not like streaming a video. They are computationally intense. They create large, sudden spikes in power demand. And when something goes wrong inside a data center, a cooling failure, a software problem, the whole facility can disconnect from the grid almost instantly. In 2024, in Northern Virginia, which is the largest concentration of data centers in the world, 60 data centers disconnected from the grid simultaneously in seconds. That created a surplus of 1,500 megawatts of electricity with nowhere to go. Imagine a large power station suddenly unable to send its electricity anywhere. The grid had to respond in real time to avoid a cascade of failures spreading through the network. That word, cascade, is exactly the right word, and it is why this podcast has the name it does. Now, I want to give you three concepts from systems thinking that I think really help explain this situation. I promise these are not abstract or academic. They are practical ways of seeing the world, and once you learn them, you start seeing them everywhere. The first is what we call tight coupling. A researcher named Charles Perrow studied industrial accidents, nuclear plants, chemical facilities, aviation, and he noticed that some systems have almost no slack in them. No buffer, no room to pause and think when something goes wrong. He called these tightly coupled systems. The electricity grid is tightly coupled. When a large load suddenly disconnects, the grid has seconds to respond. Not minutes, seconds. There is no time to call a meeting. There is no margin for hesitation. Data centers are now large enough to matter at grid scale. A single large facility can draw hundreds of megawatts of power. When it trips off suddenly, it is like a large city going dark in an instant from the grid's perspective. The system was simply not designed for that kind of sudden variability. The second concept is what I call mismatched tempos. Complex systems often get into trouble when two parts that depend on each other operate on very different timescales. And this is, I think, the most important feature of what we are seeing. A data center can be built in 12 to 24 months, from announcement to operational in under 2 years. The companies doing this, Amazon, Microsoft, Google, they move fast. The market rewards speed. The power grid does not move fast. Building a new transmission line takes 10 to 15 years, once you account for permitting, environmental review, and construction. Manufacturing a single large high-voltage transformer can take 2 to 3 years. The queue for connecting new power consumers to the US grid currently stretches years into the future. So we have a system, the data center industry, scaling at the speed of software, sitting on top of a system, the power grid, that scales at the speed of civil engineering. When two parts of a system are tightly linked but operating at such different speeds, fast one will always outrun the slow one's ability to adapt. And eventually, something gives. The third concept is what I call the illusion of resilience. We think of the cloud as something intangible, weightless, infinite. The word itself suggests it. But there is no cloud, there is only someone else's building, full of machines plugged into a grid in a specific location on Earth. When people talk about digital resilience, redundant servers, distributed architectures, automatic failover, they are talking about resilience within the digital layer. And that resilience is real, but all of it sits on top of physical infrastructure that has its own vulnerabilities. Power lines, cooling water, transformers, and now the collective weight of tens of thousands of facilities, all competing for electricity from a grid that was never designed for them. In system thinking, we call this a hidden dependency. The digital system looks autonomous, it is not. And when the physical layer beneath it becomes stressed, the digital resilience can disappear very quickly. Now, I want to bring this closer to home, because the United States is just where this problem is most visible right now. The same dynamics are playing out everywhere, including in Norway, where I live and work, and where this conversation is happening. Norway might seem like an unlikely place to have this problem. Nearly 99% of Norway's electricity comes from renewable sources, mostly hydropower. Electricity is relatively cheap. The climate is cool, which reduces the cost of cooling servers. There is a space. These are exactly the conditions that attract data centers. TikTok already operates a large data center near Oslo, drawing around 90 megawatt of power, with plans to expand. Google is building a facility of up to 240 megawatts in southern Norway. And OpenAI, the company behind ChatGPT, is planning to open a data center of up to 290 megawatts in Narvik, in northern Norway. The last one is being built by Aker, one of Norway's largest industrial groups. At full operation, that single facility in Narvik would consume close to 1% of all the electricity currently produced in Norway. Just let that number sit for a moment. One building, 1% of the country's electricity production. And analysts project that electricity demand from data centers in Norway could grow from around 1.6 terawatt hour in 2024 to 18 terawatt hours by 2040. That is more than 10 times the current level in less than 2 decades. Norway's grid operator, Statnett, already has a queue for connecting requests that exceeds available capacity. The Norwegian government has acknowledged publicly that there is considerable uncertainty about how many of these queued projects will actually be connected and when. This is exactly the mismatched tempo problem I described earlier, playing out in a Norwegian context. And there is a social dimension here that goes beyond engineering. Norway already has real debates about electricity prices, about who gets access to cheap renewable power and who bears the costs when new large consumers arrive. The data center boom is a central part of that conversation. Some communities welcome the investment and the jobs. Others ask a harder question: whose electricity is this? And whose future are we building when we hand it to the global tech industry? These questions are not unique to Norway. They are being asked in Ireland, in Sweden, in Singapore, in South Africa. Wherever cheap power and good connectivity exist, this conversation is happening. The infrastructure is global, the tensions are local, and the system connects them all. Let me give you a few numbers to make the scale concrete, because I think it is genuinely difficult to grasp without them. Right now, the data centers in the United States consume roughly 180 terawatt hours of electricity per year. By 2030, projections put that number somewhere between 400 and 600 terawatt hours. For reference, that approaches the total electricity consumption of a country like France. Data centers currently account for around 4 to 5% of total US peak power demand in summer. Within just a couple of years, that share is projected to nearly double. That is not gradual growth. That is a step change. Gartner, the technology research firm, has estimated that power shortages will operationally constrain 40% of AI data centers by 2027, not a distant projection, 2027. And the bottleneck has already shifted. A few years ago, the main constraint for building data centers was hardware. You could not get enough advanced chips and servers. Today, the main constraint is power. You can build the building, you can order the servers, but you cannot always get a grid connection in time. The grid, designed for a world that did not include AI, is becoming the limiting factor for the digital economy. You might be thinking at this point, okay, this is an engineering problem. Build more power plants, upgrade the grid, solve it. And I understand that reaction, but this is exactly where I want to push back a little. Because if you look at it only as an engineering problem, you miss the harder part. The harder part is that this is a socio-technical problem. That word, socio-technical, means that the technical system and the social system are not separate. They shape each other, and you cannot solve one without dealing with the other. Take the question of who pays for grid upgrades. This is not a technical question. It is a political and economic one. Data center companies want affordable power and generally resist being classified as the cause of the strain. Ordinary households, people who did not ask for AI data centers to be built near them, are being asked through higher electricity prices or utility costs to effectively subsidize that infrastructure. That is a social choice, and it is being made in most countries without much public discussions. Or take the question of governance. The electricity grid evolved over a century through a patchwork of regional operators, national regulators, and private utilities. It was not built to make fast, coordinated decisions about a new type of industrial consumers arriving at internet speed. In Norway, in the US, across Europe, the regulatory systems move slowly. The data center industry moves fast. That asymmetry is itself a systemic risk. And underneath all of these is a question that I think we need to sit with. When the decision was made, and it was made collectively through markets and investment and policy to build the infrastructure for a global AI industry, did anyone model what it would do to the physical systems that underpin it? The grid, the water supply for cooling, the land? Mostly no. This is not a conspiracy. It is not a failure of bad intentions. It is what happens when you optimize locally and never look at the whole. In systems engineering, we call this sub-optimization. Every company does what makes sense for its own part of the system. Every regulator manages their own piece, and the system as a whole drifts toward a place that nobody chose and nobody fully anticipated. The emergency order in the United States, the one that gave grid operators authority to cut power to data centers to prevent blackouts, is a signal worth paying attention to. It means that the people responsible for keeping the lights on are no longer confident that the growth of AI infrastructure is compatible with a stable electricity supply, not without new investment, not without new rules, and not without a fundamentally different way of thinking about how these systems fit together. The cascade has not happened yet, but the conditions for one are being assembled. Data center by data center, grid connection by grid connection, from Virginia to Narvik. Systems do not usually fail all at once. They drift, slowly and almost invisibly, toward the boundary, and then something small happens in the wrong place at the wrong time, and things move faster than anyone expected. That is a cascade. And the question that I keep coming back to is not whether it can happen. The question is whether we are developing the awareness, the tools, and the governance to see it coming before it does. That is what this podcast is about. I am Omid Razwani. Thank you for listening to The Cascade. Next episode, we pick a new story and look for the connections that are hiding in plain sight.